Air at standard condition enters the compressor at rate of 0.3 meter cube per second. It leaves the tank through a 3 centimeter diameter pipe with a density of 1.8 kilogram per meter cube and a uniform speed of 210 meter per second. Determine the rate at which the mass of air in the tank is increasing or decreasing, and determine the average time rate of change of air density within the tank. So in this situation, you need to think very carefully. So we have a tank here which is very rigid, not expandable like a balloon. So, but the fluid that we push into this tank is air. So air means it can be compressed. So and then we have an outlet here at certain volume. So means that the idea is we compress an air into a tank, and then at the same time it will release at certain speed. So we calculate, we write down we draw the free body diagram. So this is the velocity, so this is the vector n, the outside, it will going outside from the control volume. So this is the velocity at outlet, and this is the vector n. So and then we could calculate as this one. So conservation of mass, so mass flow rate at inlet must be equal to the mass flow rate at outlet. So if we calculate that one, we found that the mass flow rate at inlet is 0.369, but the mass flow rate at outlet is 0.26, so it is not the same. So means that we could simply assume that we just minus 0.3 with 0.26. So we could say that it must be an increasing of a mass in the tank, because the mass flow rate must be constant, must be conserved. So inlet is 0.369, so and then the outlet is 0.2672, so means that we have 0.1018 kilogram per second mass flow rate increase in the tank. So and then if we want to calculate according to the Reynolds transfer theorem, we could use this idea. So this is the Reynolds transfer theorem general equation. So dn dt is equal to 0 because the conservation of mass. So and then for the second terms here, okay, so as we know that B is equal to 1, so and then rho and volume will become mass. So we have a dm dt here. So and then we could calculate the value of this one. So we could have B is 1, we have rho Vn is negative V inlet, and dA is the cross-sectional area. So in some solution, people use the idea of rho and negative Q. So the Q here, we know that in our previous lecture, Q is equal to A times V. So this is A and this is V. So we could have Q here. So and then we substitute the value. And then for the second one is rho AV. So we know the area for outlet, and we know the speed at the outlet here. So if you solve this equation, you will get the dm dt is 0.1018 kilogram per second. So mean there is an increment of mass inside the tank. So these two solution is actually just to give you an idea. Sometimes you could solve problem by thinking it straightforward by using the idea of continuity equation that we learned in previous chapter. But if you want to use the idea of Reynolds transfer theorem, you still have the same value here. And then we go for B. So and then we could simplify. This is the Reynolds transfer theorem for the general one. So and then So this is the Reynolds transport theorem equation. So dn dt here is equal to 0 according to the idea of conservation of mass. So and then we could calculate this term. So it is equal to 0.01018. You could refer to the previous calculation. So and then we need to leave this term as it is, because it will give us like this one. So because here we have a 0, so we bring 0.1018 to the left hand side. So we have this one. So and then we could write as this one. So this is actually the idea of, here we have a del dt for rho and volume. So if we expand this term, we will get rho d volume over dt plus volume d rho over dt. So in this situation, we found that the volume over dt here is equal to 0, because the tank of our compressor is rigid, it's not expandable, so means that there are no changes of volume along the time. So if dv dt here is equal to 0, mean all this term can be neglected. So now we only have volume d rho dt in our calculation. So that's why in the here we just use the term of d rho over dt and volume in our calculation. So and then the volume here is constant, so and then we could calculate the d rho dt. So this is the changes of density along the time. So if we bring the velocity to the we divide it here, so and then we could calculate the d rho dt is equal 0.1697 kilogram per meter cube per second. So this is the changes of density, because it has positive sign, so means that the density inside the compressor is become higher and higher. It's become dense and denser and denser.